Please welcome Jacky and Alan.
Hello, good afternoon, everyone. Welcome to this session on leveraging the power of Python to deploy an enterprise-grade Delta lake on AWS. I'm Jacky, Solutions Architect from AWS. Okay, so maybe I stand here still. And I've been working on multiple data lake projects in before, and I really found data lake projects are often very inspiring. And one of the most successful story I would say is worked with Intel technology. So today we will have Alan as my co-presenter to share more on the data lake story and the lesson learned we have throughout the journey. For today's agenda, I will refresh everyone by giving you a really basic concept on what data lake is, and then I will pass the time to Alan to talk about some more complex idea on data lake. And he will also walk you through some really real-world use cases by leveraging different Python tools or using different library in order to tackle some really demanding requirement on some enterprise scenario. Okay, to begin with, what data lake actually is. So it is a centralized repository for storing both of your structured and unstructured data. It is a single comprehensive view of all of your data assets in your organization. Rather than storing them in different siloed data stores, you really want to store all of them in a single centralized repository. Of course, it is more than data storage. It is also open up your analytic capability. So by storing data in an open source file format, it allows you to adopt multiple different query and analytic engines and also different kinds of machine learning capability on top of your data lake. It really unleashes the full potential of your data, which is often hidden in the past. More than that is the flexibility of data movement. You can easily set up data pipeline between your on-premises data stores and the data lake. You can ingest data freely from your on-premises data store, like your MySQL database, your SQL Server, your Oracle database. And furthermore, you can also ingest data from real-time data source, like your IoT data, your clickstream data on your website. And of course, you can also move data out from your data lake to some purpose-built data store like OpenSearch, like Athena on AWS, like some data warehouse. So data lakes is actually the foundation for a really data-driven organization. You will need a data lake to consolidate your data assets. You will need a data lake to help to empower your analytic and machine learning capability. You will also need the flexibility brought by data lake so that you can move effectively. Let's dive deep into some more reasons why we need a data lake. First of all, data lake decouple the storage and compute layer so that you can scale the storage layer or you can scale the compute layer without any dependency. This means when there is any data growth, you can use a more cost-effective way to scale your storage rather than provision a larger instance in no matter your VM farm or on the cloud. By storing data all into a single place, it also allows you to run advanced analytics across all of your data sources. It also reduces complexity in the ETL tasks and the operation overhead. That means you can free up your human resources or even your computer resources to do some really meaningful and valuable analytic workloads. And we often look forward to the future, right? So there are lots of emerging database technology, AI technology, analytic technology. By adopting data lake, it is really a future-proof approach to handle your data, because it is very easy for you to find that whenever there are some new technology coming in, you can quickly integrate your data lake into those technology. Before the emergence of data lake, how we handle analytics is usually follow this pattern. So we rely on a single data warehouse which stores structured data, which is also often relational. So it works well until we found some limitation from it. First of all, it is coming from the schema. We often need to define data model and data schema before we ingest data into the data warehouse. For current situation, we often found that the business requirements change very rapidly. From quarter to quarter, from month to month, there are some new changes. And due to the emerging new technology, we have so much new data sources as well. Therefore, we really need the flexibility on the schema to adapt to these rapid changes. And this is the first limitation. The second limitation is that we often need to plan ahead of the infrastructure setup for our data warehouse. So for example, in day one, we know that the data warehouse is only used for maybe business intelligence, maybe only used for reporting. But later on, we found that it also need to handle some operational workloads, like it also need to run some ad hoc query. So we often need to over-provision our infrastructure to support our data warehouse. This limitation really paved the way to the emergence of data lake, which can handle any size of data volume in a much lower cost, and it provides you much more flexibility and scalability. Let's see how data lake address these challenges. So first of all, it has schema on read rather than schema on write. What it means is that whenever you have new data sources, you can directly ingest your data into a data lake without setting up a rigid schema upfront. That is really a big improvement. Whenever there are new changes on business requirement, you can directly ingest your data, then redesign your ETL to accommodate your new data sources. Secondly is the decoupling of storage and compute layer that I have mentioned before. The key benefits from this is that you can really scale your workload according to your actual need. This can lower your initial cost and the ongoing management effort. And lastly is that data lake, the ecosystem will often offer you lots of options in analytic tools and machine learning capability. And it often offers you in an on-demand basis, which means you don't need to plan ahead in day one. You don't need to over-provision your infrastructure to support all the future use cases that further lower your initial cost and secure your future. Another benefit is that by storing all the data in single place, you can avoid your data being distributed in multiple locations and in different data silos. Data lakes serve as the single source of truth, so you can store and analyze all of your data from all of your data sources in one centralized location. So I think I have pretty much presented all why we need a data lake and what it is. But when we talk about building a data lake, we often suggest you to build it on cloud. For example, on AWS, we provide you a broad set of tools and technology to cover the full life cycle of building a data lake. You would need to set up storage infrastructure. You will need to move your data from data source to the data lake. You will need to cleanse, prepare, and catalog your data, then configure and enforce security and compliance policies. And last but not least, you will need to make your data available for analytics. AWS is just a future-proofed platform by providing you services like Amazon S3, AWS Glue, EMR, Lake Formation, etc., which can help you to streamline every processes in your life cycle of building and managing a data lake. The rich features and the broad set of tools and technology available on AWS are often fully integrated. So you can really focus on deriving data insights from your data rather than worrying about the underlying infrastructure. In short, AWS will provide everything you need to build a data lake. Before we move on, I will spend a moment to introduce Aaron from Atal Technology. He is the Assistant Technology Manager for Atal Technology. He has worked on some really brilliant data lake projects. One of the projects delivers remarkable results to Hong Kong enterprise customers. We successfully saved 7 up to 15% of energy costs for this customer on a single building. I'm excited to have Alan to share more on data lake with us. And Alan, the floor is yours. Thank you.
So in Atal, we built the data lake on. Okay, thanks, Jacky. So in Atal, we built the data lake on Amazon about 5 years ago. It improved the data analytics efficiency a lot. For example, the data pipeline development time reduced a lot so that our data team can focus on the actual analysis. And to prepare for the future data explosion, we further upgraded the data infrastructure to a modern architecture 2 years ago. But before exploring the new data lake architectures, I would like to share some pain points I've encountered when operating with the traditional data lake. For example, for traditional data lake, there are limited ACID transaction support. So in many scenarios, it can actually corrupt the data set. For example, the lack of atomic operations, meaning during the partial failure, an inconsistent state could happen in the table. Also, without the transaction support, the race condition between multiple writers could happen when we want to have multiple writers to operate on the same table simultaneously. So this all situation could lead to incorrect analytic results and wrong business decisions, and it is not ideal. Furthermore, traditional data lakes has very limited update and delete capabilities. We usually require rewrite entire files to make small changes, so it is very inefficient and costly. And for example, when we need to implement GDPR compliance, or we implement a slowly changing dimension, which is a common data warehousing pattern, we need to do many update and delete operations on the table. And this limits the usefulness of data lakes in certain enterprise use cases. And finally, it's about the schema evolutions. For example, traditional data lake does not have a built-in schema management features. So when we need to add or modify column in a table, we need to care about if it breaks the downstream processes. Also, there are no standardized way to track schema version. It makes it very difficult to evolve the data structure because in general, the business changes rapidly. We need to update the data, we need to update the data lake, and we need to care about whether it breaks the downstream processes. So we now have some idea about the limitation of traditional data lakes. So let's see how Delta lakes can resolve them. First of all, Delta Lake has ACID transaction support. It manages the transaction log internally as a sequence, and every transaction gets a unique version number. As you can see, that it provides atomic behavior and proper isolation immediately because atomicity is achieved is because change a record as an atomic unit in the transaction log. And also for each transaction log, it provides sufficient information to link to the underlying data set, meaning readers can see a consistent snapshot during the query. Secondly, Delta Lake has a rich DLM support. For example, it has a native support for update and delete. These simple SQL statements shown here are actual code that is executable on Delta Lake. Although for some operation, we might still need to rewrite entire files, but you can see that Delta Lake encapsulates all tedious file manipulation details. And finally, it's about the features around schema evolution and enforcement. For example, Delta-rs automatically validate incoming data against the defined schema. It prevents data quality issue before it impacts the downstream process. Also, the schema evolution is handled gracefully. For example, when we need to add or delete or modify a column, we don't need to care more about the downstream processes because it won't break the existing pipeline. And apart from resolving the pain points I've mentioned, Delta-rs also provide other valuable features to tackle common data warehousing pattern. But for example, time traveling and some query performance optimization. So we have discussed some useful features provided by Delta-rs. So let's see how we can implement them in few lines of code. We use the package called Delta-rs for the demonstration. So here we are going to create a Delta table. As you can see that this API Delta-rs provide an intuitive API for us to manipulate the table and the data set. To create a table, we can simply define the schema in an intuitive way, and then we call the Delta table.create, and that's it. And after that, we might want to ingest some data into the table. Delta-rs has a very smooth integration with pandas. So when we append data into the table, we can prepare the data in pandas first and then load them into the table. You may notice that once we write data in the data lake, the metadata have been changed. For example, we get a newer table version, and the file count of the table is now 1. If we further append more data into the table, the version get updated. So the data lineage is also managed by the Delta lake. And finally, we mentioned before that in traditional data lake, we have some difficulty to perform update or insert. So here in Delta lake, you can see that the update workflow is now very straightforward. What we need to do is to first, of course, prepare the update. And then what we need to do next is to instruct Delta-rs how the upsert or update should perform. And it's done. Delta-rs handle all the other, for example, the file lifecycle and role manipulation for us. And there are many other useful features. For example, we can read a specific version or to restore a specific version from history. And now we have more understanding on what Delta-rs can do. So in the following slide, I will talk about the data we have and also the Delta-rs architecture in AWS. So my team focus on developing a smart building solution. Our goal is to integrate all data generated from a commercial building. So for example, in a typical office building, we have more than 10 subsystems to integrate. And we save about 1 billion records a day. The raw data size is about 300 gigabytes per day. So once we have collected this data from various systems, we store them as raw as possible to the data landing zone on Amazon. And the left-hand side is the data landing zone I've just mentioned. The data are then processed multiple times in the data lake. We classify these tables into 3 main categories. From bronze table, which is actually the raw data, but in Delta-rs format, to gold table, and they are augmented, aggregated data sets that is ready for application or analysis use. And around the data lake, you can see we have 2 computation engines. The purple one is the Spark that runs on Amazon YAML, and the orange one is a simple Python application with Delta-rs installed that deployed to a Kubernetes cluster. We will talk about these 2 engines a bit later. So then after we have processed all the table, all the data in the data lake, we will organize them into Delta catalog using Amazon Glue. And this table catalog are then served using a field analytic engine, for example, Athena for ad hoc query and Redshift Spectrum. And thanks to the Amazon native integration, so we can discover and also use data directly on, for example, QuickSight, a BI tools, so that we can discover insight from data, and SageMaker, a fully managed service by fully managed machine learning services. So let's talk about the two engines around the data lake. The first one is to handle a large-scale data set. We use PySpark, and it is run on a EMR serverless cluster. EMR is a fully managed Spark environment. It handles all the cluster management for us. So it reduces the operational overhead and also let the data team focus on the data processing logic. And the elastic nature of EMR allows us to scale the cluster based on the workload demands, so that we only pay for the actual compute resource we need. And there are some native integration between other Amazon services, for example, S3, the storage, Glue, the data catalog, and lake formation for the data governance. It provides a comprehensive data platform, and it enables end-to-end data pipeline with minimal custom integration work. So with this tech stack, we can use it to manipulate data sets from terabyte scale to even exabyte scale. We can also use it to run both batch and streaming processes in a unified framework, Spark with Delta Lake engine. And this way, we can reduce the number of lines of code to maintain, and hence, it encourages real-time analysis. Another engine is to handle small to medium-sized data set. It's simply a simple Python program with Delta-rs package installed. Delta-rs provides a lightweight Raspberry implementation of Delta Lake protocol. And we have already seen that how intuitive those APIs are in previous example. And these Python applications are deployed on a Kubernetes cluster. And to be more specific, it is on a Fargate profile. The surface nature of Fargate profile allows us to focus on the workload only. For example, when we need to run multiple pipelines at once, we can simply scale out. And once all the pipeline has been complete, we can scale the compute resource down to 0 to save cost. So in this engine, so we can use it to manipulate small to medium-sized data sets with really low cost, because all change data can be loaded on memory. And it avoids the operation like data shuffling, which is required in many distributed computation frameworks. Also, it allows microservices to read or write the Delta table directly, so that it simplifies the overall architecture and operational overhead. So now we have Spark, we have Delta-rs on hand, and they have their own advantages. So how should we choose in different situations? One way we can make the decision is to determine what feature sets we need. Delta-rs provide all the basic operations for interacting with the table. However, this project is relatively new. So some advanced features, for example, change data feed, which is crucial for stream processing, are still being developed. Also, there are some schema modification. It is also underdeveloped. So if you need them, then we might go to Spark. Or if we only need basic operation, Delta-rs would be a very good choice. And another way to design is to estimate the data size we need to process. For example, if we can fit the whole table into the memory, then of course we can use Delta-rs to handle all the operations, do the ad hoc analysis. But in general, it is not the case because we usually can't fit the whole table into the memory. So we may ask another question that can we fit only one day data in memory? If this is possible, then we may choose the mixed approach, meaning we use the Delta-rs run on a Python application to append data to the table for the daily ETL job. However, for general data manipulation, for example, ad hoc analysis on the whole table, we will use Spark engine to perform the analysis. And finally, if data is too large to fit in memory anyway, then we might need to use the Spark on YAML with Delta engine. It unleashes the full power of Delta Lake, and it can process the dataset at any scale. So that's it. I hope it helps lower the barriers to the Delta Lake engines for you. And thank you.
Thank you. Do we have any questions for the two speakers? We have about 4 to 5 minutes. It's pretty quiet crowd after lunch. Okay, here's one.
Sorry, I may ask a kind of fundamental question because I don't know what is the next one is not that. But based on what you said, it seems that that's fine. Sorry. So data lake is like you have to log all the transaction changes instead of like actually doing the changes to the database, right? Is it what it's doing?
Not exactly. So let me go through the slide in the previous slide. So for example, in this code example, we still focus on the actual changes. For example, here we prepare the data, we explicitly write data into data lake, and that's it. And internally, data lake helps you to manage all the transactions in the metadata layer. And of course, it also handles the underlying file changes or life cycle. So we still focus on the operation instead of all other transactions or other features provided by data lake.
So the output of the data is it is a kind of special format. Actually, it's some kind of Delta Lake kind of data set. So do we need to do some kind of cleanup every time Delta Lake finish something? Or is it basically, it is just, oh, this is the kind of new standard, we call this Delta Lake. So every time we use it, it's just like traditional data lake.
I think it's quite similar to traditional data lakes. So again, for example, this example, or maybe I give the SQL statement previously. These SQL statements are executable on Delta Lake. So you can see we really focus only on the operation, and that's it. So internally, Delta Lake might have more to do because we need to manage the transaction, the unique version. For example, also the data raising, there are many other stuff to handle. But to us as a developer, we only focus on the data manipulation only.
Can you discuss the cost structure of the traditional data lake approach versus the Delta lake approach?
Cost, you mean?
Cost savings, like operational.
I think the cost is, in terms of storage, we use both S3. For example, we can use both S3 as the storage layer for traditional data lake or the Delta lake. So in terms of the storage layer, it would be similar. However, you can see that we manage the whole history of the transactions. It might consume a bit more storage when we use transactional data lake. But for the compute engines, for example, in a very typical situations, we use the Spark engine run on YAML. It's basically the same for both traditional data lake or Delta lake.
Thank you, Alan and Jacky. Let's give them a round of applause.